Hello everybody, my name is Farhad Ghanipur from TU Eindhoven. Today I will present the paper entitled Ultra-Local Nonlinear Unknown Input Observers for Robust Fault Reconstruction. The presentation is organized as follows. First I will give an introduction to the problem, then the mathematical problem formulation. Next I will talk about problem solution, which follows with simulation results. Finally, I will conclude and talk about future works. First, introduction. Nowadays, there exist numerous high-tech systems. In my PhD project, I'm involved with two of them: wafer handler robots of ASML and industrial printers of Canon. For these high-tech systems, there is a demand for reliable operation, which can be achieved through predictive maintenance. A fundamental element for predictive maintenance is fault estimation. So we are focused here in fault estimation of high-tech systems which are mostly nonlinear. So let me formulate the problem mathematically. First, consider the system dynamics, in which X is internal state, U is input, and Y is the output. In dynamics, these two terms corresponds to linear part, and G shows the nonlinearity, which is globally Lipschitz, and alpha is Lipschitz constant. I should mention that S is shows the nonlinearity appears in which equation, and V shows the nonlinearity is a function of which state. The last terms in process and in the measurement shows the contribution of fault. F here is an unknown fault vector, which consists process fault and sensor faults. Also, we assume that the fault vector is R times differentiable. So here we would like to estimate this fault vector knowing system model and real-time input and output data. Our approach is that we consider an internal model for the fault, ultra-local fault model, which is a chain of integrators. And in that, the higher order of fault derivative is considered to be zero. So this model gives an approximation of F as F bar. Considering this model, if we augment system states with fault and its derivative up to order R-1, we can get augmented dynamics as shown here. In this augmented dynamics, because we haven't considered a higher order of fault, actually the R derivative of the fault in this model, it enters augmented dynamics as a disturbance. Then we construct a nonlinear observer to estimate augmented states, XA. The nonlinear observer dynamics is shown here, in which Z is state of observer, and N, G, L, and M are defined like this, and here E, K, and J are independent design matrices, and X hat A is given by this equation. I should also mention that we are not interested on all X hat A, but we are interested to the part which corresponds to a fault estimate F hat. To come up with a design method, we need to define aerodynamics of this nonlinear observer, X hat A minus XA. Using these relations, it is equal to Z minus MXA. And then if we take a time derivative of that, we have estimation aerodynamics, which has a linear term, NA, and a term because of nonlinearity, in which delta G is the difference of nonlinear term in the observer and the nonlinear term in augmented system. And the last term is because of fault model mismatch. This brings me to problem formulation that we would like to solve. So we have the system, we augment it with an internal model for the fault. For this augmented dynamics, we construct a nonlinear observer and derive its aerodynamics. And then the problem is that to design E, K, and J such that we have input to state stability of aerodynamics, ISS of aerodynamics with respect to fault model mismatch. And because we are interested in performance of fault estimation, so we are interested in fault estimation error, we seek to have finite and minimal L2 gain from fault model mismatch to fault estimation error. Now, problem solution. First, ISS of estimation aerodynamics. Remember aerodynamics, we consider a Lyapunov function in a quadratic form. If we take a total derivative with respect to time, it can be shown the Lyapunov derivative is upper bounded by this, in which delta is defined here. These two terms corresponds to linear part, and these two terms corresponds to nonlinearity. So here, if we have delta negative definite and fault model mismatch is 0, we have globally asymptotically stability for E equal to 0. And if Fr is not 0, by taking norm of right hand side of this, it can be shown the ISS gain with respect to Fr is like this. And here theta is between 0 and 1, and lambda mean shows the minimum eigenvalue of minus delta. So here we only need delta to be negative definite. But due to numerical issues, instead we solve this equation, this inequality, in which epsilon is given and it is a small positive number. Now we need to convexify this inequality and find an LMI condition. Using these two change of variables and short complement, we can get it and come up with first proposition. If there exists P, R, Q, and J satisfying this LMI, in which X and X12 depend on augmented dynamics and design matrices, then the aerodynamics is ISS, and the ISS gain from fault model mismatch Fr to estimation error E is upper bounded by this value. Now we go for performance requirement on fault estimation error. For that, we use Hamilton-Jacobi inequality, which gives an upper bound of L2 gain, and try to convexify that. And it gives us the second proposition. If there exists P, R, Q, J, and ρ satisfying this LMI, then the L2 gain from Fr, fault model mismatch, to fault estimation error is upper bounded by square root of 2ρ. As a final theorem, we come up with a semi-definite program in which we minimize L2 gain from fault model mismatch to the fault estimate error, subject to an LMI for ISS and another one for L2 gain to be bounded. If we solve this optimization problem, we have and find the optimizers, we have designed the observer for fault estimation, and also we have the results of mentioned propositions. So the ISS gain from fault model mismatch to the estimation error is upper bounded by this value, and the L2 gain from Fr to fault estimation error is upper bounded by a square root of 2ρ star. Now, simulation results. We have applied the proposed method to a benchmark system, which is a single link robotic arm with a Revolute elastic joint. This system is taken from work of Marius Policapro and Thomas Parisani. The schematic of the system is shown here, and its motion equations are shown here. This system has 4 states: motor and link positions, angular positions, and velocities. And the nonlinearity in this system is because of gravity effect on the link. And the measurement of this system is positions of motor and the link. And the equations of this system can be transformed into the form that we use. And for this system, we consider two fault scenarios. The first one is actuator or motor fault, and the second one is a motor sensor fault, which is an encoder fault. We have simulated two mentioned fault scenarios and applied our proposed method to estimate those faults. First, actuator fault. In this plot, the actual fault is shown in blue, and our estimation, the estimation of the fault using our proposed method is shown in red. And you can see the actual fault is a sinusoidal fault, and it is small in magnitude. And our proposed method can estimate it accurately. For the second scenario, we have simulated a constant fault, and because for this fault model mismatch f dot is 0, our proposed method can estimate it with 0 error. So it gives us a perfect estimation. Last but not least, let me conclude the presentation. Conclusion. We propose a method for time-varying actuator and sensor faults estimation in nonlinear systems. We use an internal model for fault vector, which allows us to guarantee 0 fault estimation error for some cases when fault model mismatch is 0. And we give a semi-definite program to design fault estimator subject to ISS of estimation error dynamics with respect to fault model mismatch, and finite and minimal L2 gain from fault model mismatch to fault estimation error. And simulations for the benchmark illustrate the performance and potential of the proposed method. Finally, as future works, we can consider including model uncertainties, external disturbances, and measurement noise. Thank you for your attention. Ask any question you might have. And if you are also interested in my work, you can reach to me via my email, or you can find me in LinkedIn.